This is Dr. Shankaraiah, Department of Physics. So today I am going to discuss about Module 3 Lasers and Fiber Optics, in which I am going to discuss about topic numerical problems on lasers. So in the last lectures, 4 to 5 lectures, I have discussed about lasers theory. Now I am going to discuss about numerical problems based on the theory. So understanding theory, then how can we apply the theory to solve some problems on these lasers? So the first numerical problem on this chapter lasers is find the relative population of the two states in a ruby laser that produces a light beam of wavelength 46943 angstroms at 300 Kelvin. Okay. So we have to find the relative population of two states. We have to find the relative population of two states in a ruby laser. So they have given us ruby laser, and in ruby laser if there are two states N1 N2, for example. So ruby laser has two states N1 and N2. So let's say N1 is the lowest energy state and N2 is the excited state or metastable state. Okay, so let us say N1 is a ground state and N2 is the metastable state, because metastable state we need to achieve population inversion, right? So this is metastable state. Yeah. So now we have to find the relative population between these two states in a ruby laser that produces a light beam of wavelength. So you are going to get a laser beam of wavelength 6943 angstroms. Okay, and temperature they have given as 300 Kelvin. Okay, so the given parameters, wavelength. So you write here wavelength of the beam lambda is 6943 angstroms, and the temperature T temperature is 300 Kelvin. Okay, with these input parameters, we are going to find the relative population between these two states N1 and N2. We know that there is population inversion state and there is normal state. In normal state, and this state is also called equilibrium state. Normal state or equilibrium state, we know that N1 greater than N2. That means more number of atoms exist in the ground state compared to the metastable state. If this is in normal state or equilibrium state. In inverted state, okay, in inverted state or non-equilibrium state, we know that N2 is greater than N1. Okay, so we need to find out the relative population, so that whether it is in the whether there is any population inversion or is there normal state or inverted state. So to find out that, we are going to find out the relative population between these two states given in ruby laser. Okay, that is producing the laser beam of 6943 angstrom wavelength. Okay. Yeah. So formula for that, the population ratio or relative population between these two states N1 N2 is given by this N1 N2. Okay, so N2 by N1 is equal to exponential of minus E2 minus E1 by KT. K is nothing but Boltzmann constant here. Okay, so K, I'm writing here K, or you can write it as KB, so that you remember it what exactly is. KB is Boltzmann constant. It's a universal constant, so you need to remember the value of Boltzmann constant KB. So that is 1.38 into 10 power minus 23 joules second. Okay, so now, yeah, so the relative population N2 by N1 is exponential of minus of E2 minus E1. So let me write here. So it's N2 by N1 is equal to exponential of minus E2 minus E1 by kVt. Okay, so first we need to calculate E2 and E1, energy of state N1 and energy of state N2 are state 1. Okay, so this is state 1 and state 2. So we are going to find the energies of these two states first. So that is E1 and E2. If you know E1, E2, you can calculate the difference E2 minus E1, and then Boltzmann constant is a universal constant, T is temperature they have given it. So we can calculate the population ratio, right? Okay. So to calculate that, they have not given E1, E2, but we need to calculate that. So using this formula, E2 minus E1 is equal to H nu. Okay. We know that the difference between these two energy states, okay, E2 minus E1 is always the photon. When an atom decays from the metastable state to ground state, it relieves a photon, right? It emits a photon, and the energy of the photon is H nu, which is equal to E2 minus E1. Okay, so using this E2 minus E1, which is equal to H nu, or nu is frequency. Okay, here nu is frequency. Okay, so I can write the frequency in terms of wavelength. So C, frequency is C by lambda. Nu is C by lambda, so H nu is Hc by lambda. So now I know lambda, they have given input parameter lambda as 6943 angstroms. And I know C is velocity of light, right? C is nothing but velocity of light. I know the velocity of light, it is also universal constant. H is also Planck's constant, this is also universal constant. So H and C I know, H is Planck's constant, right? H is Planck's constant. Okay, so now I am going to substitute the Planck's constant, velocity of light, and wavelength of light. Okay, if by substituting all these values, I am going to get the energy of the photon emitted H nu, which is actually indirectly equal to E2 minus E1. Okay, so I have substituted 6 minus 6.626. Okay, so Planck's can substitute the value of Planck's constant 6.626 into 10 power minus 34, and velocity of light in meters per second 3 into 10 power 8. Okay, divided by wavelength. Wavelength they have given as 6943, and we are converting into meters. Okay, from angstroms. So 1 angstrom is 10 power minus 10 meters. 1 angstrom is equal to 10 power minus 10 meters. So that is why I have here 6943 angstrom it should be, but I have converted angstrom into meters. So 6943 into 10 power minus 10. Okay, so first calculate the numerator. First, we are going to calculate the numerator 6.626 into 10 power minus 34 into 3 into 10 power 8. Once we calculate the numerator multiplication, what we do, then take the denominator. Okay, multiplication after the divide by 6943 into 10 power minus 10 angstroms. So always in calculator, when we are using calculators, you better put this parenthesis. Always use these brackets. Okay, so all the numerator must be inside a bracket. Okay, then divided by this. If you want to use all it at once, use these parentheses. Write all the numerator in parenthesis, and then divided by, write all the denominator in parenthesis. Then you will get the correct answer. Okay, so now we have E2 minus E1 value. Okay, E2 minus, once we have E2 minus E1, the energy difference between these two states, E1, E2. Now we are going to substitute in this equation. N2 by N1 is equal to exponential of minus E2 minus E1 by kBT. Okay, so exponential of minus E2 minus E1 is given minus of E2 minus E1. So the minus remains here. So 2.85 into 10 power minus 19 divided by kBT. kB is Boltzmann constant 1.38 into 10 power minus 23 into temperature is given as 300. Okay, so again, okay, put a parenthesis to the numerator and put a parenthesis to the denominator, then take exponential. Okay, in the calculator take exponential, then a bracket, again there is you put a parenthesis, then numerator in a parenthesis divided by denominator in a parenthesis, then you will get the correct answer. If you do not take the proper parenthesis, you will get a wrong answer. Okay, yeah. So the population, relative population between these two states is 8 into 10 power minus 31, very small. The change between these two states. Okay, so here we have calculated the relative population between the two states N1 and N2 in a ruby laser that emits light laser beam of wavelength 6943 angstroms at a temperature of 300 Kelvin. Okay, let us look into the second problem on lasers. Okay, the second problem on lasers is for a helium neon laser. So here they have mentioned that it is a helium neon laser. It distances 1 meter and 2 meters. So they have given two distances. D1 is 1 meter, D2 is 2 meters. So for a helium neon laser at 1 meter and 2 meter distances from the laser, the output beams for diameters. So they have given diameters. Diameter A1 which is 4 millimeters and diameter A2 which is 6 millimeters. Calculate the divergence. Okay, so for the helium neon laser, they are asking us to calculate the divergence of the laser beam given at two different distances, 1 meter and 2 meters. At 1 meter, you have one diameter, at 2 meters, you have another diameter. So using these input parameters, so these are the given parameters, so given data. So D1, D2 are distances. So distance D1 and D2, and these are the diameters. A1 4 millimeters and A2 6 millimeters. Okay, so we know the divergence formula. Okay, divergence is nothing but the spread of light. Okay, we know that the spread of laser beam is very small. It is always in the order of milliradians, right? So yeah, so the divergence formula is this: theta is A2 minus A1 by 2 into D2 minus D1. Okay, so A2, A1 are diameters. You can write this formula in terms of radius also. In terms of radii, theta is R2 minus R1 by D2 minus D1. Okay, because diameter A is radius, 2 into radius is diameter. So if you want to use radius, if you want to write in terms of diameter, you can use this formula. If you want to write in terms of radius, you can use this formula. Okay, so radius is nothing but diameter by 2. You can write that. So it is easy to understand this formula. So here R2 minus R1 by D2 minus D1. But if you want to replace R by A, so you have to write here A2 by A2 by 2 minus A1 by 2. So that will come into denominator. So that is why it becomes A2 minus A1 by 2 into D2 minus D1. Okay. Yeah. So now they have given diameters and distances, so it is easy to calculate the divergence, right? So A2 minus A1, A2 is 6 millimeters and A1 is 4 millimeters. So 6 minus 4, and I'm converting into meters because the other ones are in meters. Distances are in meters. So 1 meter is 10 power minus 3 millimeters. So 1 meter is 10 power minus 3 millimeters. Right? So that is why I have here 10 power minus 3, because I have converted in meters. So I can write down here also. 4 into 10 power minus 3 meters, 6 into 10 power minus 3 meters. Okay, so it is easy now. So 6 minus 4 into 10 power minus 3 divided by 2 into D2 is 2 meters and D1 is 1 meter. So all are now in meters. Okay, again we can do this using calculator. It's easy to do here. Okay, so whatever we get here is 10 power minus 3 radian. 10 power minus 3 is 1 milliradian. So I'm writing here directly 1 milliradian as the answer. So for a helium neon laser at 1 meter and 2 meter distances from the laser, the output beam spot diameters are 4 meters and 6 meters respectively. Then the divergence of this laser beam is 1 milliradian. Okay. So this is the divergence formula in terms of diameters, and this is the divergence formula in terms of radii. So in the first problem, we have learned about the relative population of a given laser between two states N1 and N2. Now we have calculated the divergence of a given laser. So if I have a laser beam coming out at different distances, I want to look at the spread of this laser beam. So you can use this divergence formula to look at the laser beam, and we always find that the laser beam divergence is very small. It is around 1 milliradian. So coming to the third numerical problem, a helium neon laser emits a light at a wavelength of 632.8 nanometers and has an output power of 2.3 milliwatts. how many photons are emitted in each minute by this laser when operating. So they have given helium neon laser and a wavelength. Okay, so given wavelength lambda. Okay, you can write wavelength lambda is 632.8 nanometers. Okay, and what have they given? They have given output power. Output power is 2.3 milliwatts. They have asked to calculate how many photons are emitted in each minute by this laser. So they are saying that one laser, a helium neon laser emitting a laser beam of this wavelength 632.8 nanometers, and the laser beam output power is 2.3 milliwatts. So for such a laser beam, how many photons are emitted for each minute? That is what we are going to calculate. Okay. So these are the given input parameters, wavelength and output power. Now we have to calculate how many number of photons are emitted each minute. We have to calculate not per second, per minute we have to calculate. Okay. Fine. So the given wavelength of the laser beam is 632.8 nanometers. We are going to convert these nanometers into meters. So we know that 1 nanometer is 10 power minus 9 meters. Right? So I am going to substitute here 632.8 into 10 power minus 9 meters. Okay, so that will become 6,000. Yeah, that will become this 6,000 because I'm going to move this to right side. So there is a minus 1 comes 6,328 into 10 power minus 1 into 10 power minus 9. So that will become 10 power minus 10. Okay, so the wavelength is 6,328 into 10 power minus 10 meters. The output power PO you can write. Output power PO is 2.3 milliwatts. Now we have to calculate the number of photons emitted. So to calculate this, first I am going to calculate the frequency of photon emitted by a laser beam. Okay. So first I am going to calculate the frequency of photon emitted by a laser beam. So using this formula, nu is equal to C by lambda. Nu is frequency. We know that frequency nu is given by C by lambda, where C is velocity of light. So 3 into 10 power 8 divided by lambda, 6,328 into 10 power minus 10. Okay. First, we are going to calculate the energy of photon first. Energy of photon is h nu. Okay. So to calculate h nu first, we need nu. So that is why I have calculated nu, which is frequency C by lambda. So C is velocity of light, lambda is wavelength. So I know these two values. So I have substituted and I get the answer 4.74 into 10 power 4 h. This is frequency because that's why units are hertz. Now, energy of a photon is h nu. We know a nu. So multiply with h. H is 6.626 into 10 power minus 34 into nu. Nu is 4.74 into 10 power 14. Okay, so we'll get an answer. Energy of a photon is 3.14 into 10 power minus 19 joules. Now we know the energy of each photon, which is 3.14 into 10 power minus 19 joules. Now, energy emitted by the laser they have given, which is PO, output power, is 2.3 milliwatts. Okay, so we are converting into watts again. So 2.3 into 10 power minus 3 watts, or you can convert now. We can write this in terms of joules per second, or joule second inverse, or joules per second. You can write. So 2.3 into 10 power minus 3 joule per second. Okay, per second you can write second inverse. Okay, now 2.3 into 10 power minus 3 joules per second. But I want to calculate per minute. Okay, each minute has 60 seconds, so that is why I multiplied with 60. Now it becomes joules per minute instead of joules per second. Now I have it in joules per minute. So 2.3 into 10 power minus 3 into 60. This 60 came because 1 minute is 60 seconds. Fine. Okay. Now the number of photons emitted is output power divided by the energy of each photon. Total output power. What is the output power of the laser beam? So that is given as 2.3 milliwatts. Okay. Now we know the laser beam is nothing but it is containing so many number of photons. So total output power divided by energy of each photon. Then you will know the total number of photons. Right. Laser beam is nothing but the many number of photons. So you are getting number of photons coming out. That is nothing but laser beam. And if you they have given already what is the output, total output power, and if you know the energy of each photon, total output power divided by energy each photon, will give you the total number of photons. So that is why we have used the formula. Number of photons is output power divided by energy of each photon. So output power is 2.3 into 10 power minus 3 into 60, because we are going to calculate the number of photons per minute divided by the energy of each photon, 3.14 into 10 power minus 9. So you are getting 4.39 into 10 power 17 photons per minute. So per minute we are getting these many number of photons of in this helium neon laser, which is emitting 6328 angstrom laser beam with output power around 2.3 milliwatts. Okay. So here we have calculated the number of photons that are emitted by this helium neon laser beam with the output power of around 2.3 milliwatts. Okay. So let us look into the fourth problem. Okay, the fourth numerical problem on lasers is solve the wavelength of emitted radiation from gallium arsenide, which has a band gap of 1.44 electron volts. Okay, so what they have given is, they have given us the band gap. Band gap Eg is equal to 1.44 electron volts. Now we have to calculate the wavelength lambda. Okay, so band gap is nothing but the difference between these two energies. So this is E1, for example, and this is E2, and the difference between these two states, E2 minus E1, which is equal to, which is delta E, we call, or you can call this as the energy gap, which is equal to H nu. The E2 minus E1, which is the difference between these two states. Okay, let me write down this arrow like this, okay, going down. So E2 minus E1, which is equal to the gap between these two energy state, is energy gap Eg, which is equal to energy of a photon emitted. Okay, when atom goes from the excited state to the ground state, it emits a photon, right? It emits a photon of energy E2 minus E1, which is equal to energy gap. Fine. Okay, so now we have to calculate the wavelength of this emitted radiation or emitted light. So the energy gap Eg is nothing but H nu, or you can write H nu. Nu is the frequency, right? So energy gap is H nu. So our Hc by lambda, where nu is frequency, where lambda is wavelength. We have, okay. So Hc by lambda, H is Planck's constant, C is velocity of light, lambda they have given as 1.44 electron volts. Okay. So 1.44 electron volts is the energy gap they have given. So you can convert these electron volts into joules. 1 electron volt is 1.602 into 10 power minus 19 joules. So 1.44 into 1.602, you can write 1.602 into 10 power minus 19 joules. So you are going to get this energy gap in terms of joules. So using this formula, we want to calculate lambda. Okay. So lambda is equal to Hc by Eg. Eg is energy gap. Okay. So substitute H, Planck's constant 626, you can write this as 6.626 into 10 power minus 34, Planck's constant velocity of light 3 into 10 power 8. Put all of them in parenthesis, inside a parenthesis. Numerator must be closed in a parenthesis, and then denominator is lambda 1.44 into 1.6 into 10 power minus 9. So 1.44 into electron volts are converted into joules. Okay, 1 electron volt is this. So you are going to get 8633 into 10 power minus 9, 10 meters or 8633 angstrom. So this is the wavelength of the beam that is emitted by this gallium arsenide laser, which is having a band gap of 1.44 electron volts. Okay. So we have worked on different types of problems on lasers. I think we are going to look at one more problem on lasers, and then we are going to complete different variety of problems on lasers. Okay. Yeah. So the fifth problem on lasers is that a semiconductor laser diode has a wavelength of 1.455 micrometers. A semiconductor laser diode has a wavelength of 1.55 micrometers, estimates its energy gap in electrons. Given is lambda 1.55 micrometers. You can convert into meters, 1.55 into 10 power minus 6 meters. And we need to estimate energy gap Eg. Okay. So we already know the formula. We have worked out in the earlier problem. Energy gap is given as h nu, because we have discussed also, if you have two energy states in E1 and E2, if an atom decays to the ground state through an emission, decay to the ground state by emitting a photon of energy h nu, thus energy h nu is equal to the energy gap Eg, or E2 minus E1. So, okay, it's nu is frequency, you can write in terms of lambda, because lambda is given here as a input parameter. So I am converting nu frequency to in terms of lambda, so that is c by lambda. So hc by lambda, I have to estimate energy gap. So I can directly substitute all these values: Planck's constant, velocity of light, and wavelength. Okay, so velocity of light we know meters per second, wavelength is given, so we've converted into meters. 1.55 micrometers is equal to 1.55 into 10 power minus 6 meters, and we need to estimate the energy gap Eg. So Eg is hc by lambda. Substitute the value of h, which is 6.62 into 626 into 10 power minus 34, and velocity of light is 3 into 10 power 8. Put all of them in parentheses. Very good here. So now denominator is lambda, which is 1.55 into 10 power minus 6 meters. Okay, so this is energy gap Eg. So do the calculations. So finally you are going to get the energy gap in electron volts. So first you get the result. Then you divide this by 1.66 into 10 power minus 19, because we need to get the energy gap in terms of electron volts. Okay, so 1 electron volt is 1.602 into 10 power minus 19 joules. If you want to convert these joules into electron volts, okay, so I already have joules, so better divide this by 1.66 into. So I want to write now in terms of electron volts, then whatever answer you get, divide this by 1.602 into 10 power minus 19. Then you can write in terms of joules, you can write in electron. So 0.8 electron volts is the answer for this numerical problem. Okay, to summarize, we have worked 5 different problems on lasers, starting with the relative populations, right? Yeah, so to summarize, first we have worked on 5 different problems on lasers, right? So the first problem is to find out relative population between two energy levels. Relative population between two energy levels n1 and 2. So the formula is for this is n2 by n1 is equal to exponential. You can write exponential like this also. Exponential of minus E2 minus E1 by kBt. Okay. So this is exponential to all this. Exponential of minus E2 minus E1 by kBt. So this is the relative population between two energy levels E1 and E2 in a given laser. And the second problem we have calculated is the second numerical problem. Numerical problem is, yeah, so divergence of a given laser. So divergence of a given laser. Divergence of a given laser. Population version in a given laser. Divergence of a given laser. Divergence is given by theta is R2 minus R1 by D2 minus D1, or you can write in terms of radii also, A2 minus A1 by 2 into D2 minus D1, where R1, R2 are radii, D1, D2 are distances. Here A1, A2 are diameters, D1, D2 are distances. Okay, so these are the two. Third problem which we have calculated is to calculate the number of photons emitted. Okay, so the third problem is number of photons emitted in a given laser with some output power. Okay, so number of photons emitted. Okay, so number of photons emitted, we need to, for this we need to know the output power PO divided by energy of each photon. Energy of each photon. Why do we need to know the energy of photon? The output power is nothing but the photons. Light is nothing but made up of many number of photons. So output power divided by energy of each photon, then you will get the number of photons emitted per minute. Okay, so this is what we have calculated. So for that, first what we have done, energy of each photon is nothing but h nu. So what we have done, we have first calculated nu c by lambda, and then h nu, we have calculated h nu, so hc by lambda. Once we have calculated h nu, then what we have done, number of photons equal to output power PO divided by energy of each photon into 60 minutes, 60 seconds, because per minute they have asked to multiply it by 60, so that, and then whatever number of photons we are getting is per minute instead of per second. So this is third problem. The fourth one which we have calculated is to calculate the wavelength of a given laser beam. Okay, so wavelength of a given laser beam. So for that, what we have used the energy gap formula. Energy gap formula Eg is h nu, E is h nu, or Eg is h nu, or E2 minus E1 is also h nu. Okay, so you can write this as hc by lambda, because nu is frequency, you can write in terms of c by lambda. So then from this equation, we have written it as lambda is equal to hc by Eg. Then we have calculated this energy wavelength here, and then in the last problem, fifth problem, we have calculated energy gap directly. So energy gap is h nu, which is equal to hc by lambda. So we have substituted the Planck's constant and velocity of light and wavelength, and then we have calculated the energy gap of a given laser beam. So these are the 5 numerical problems on lasers. Now in the next class, we will start discussing about fiber optics. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.